In section 7.2, we're going to look at sampling distributions of sample proportions. Alright, our goal here is to anticipate the shape, the center, and the spread of a sampling distribution of sample proportions without having to do a simulation. They take a long time and a lot of effort, so we wouldn't be able to make those predictions without doing all that. So let's look at this candy machine applet. There it is, filled with Reese's Pieces. And it's taken a sample down here. And I want you to get comfortable with the verbiage here, all right? So in the terms of this Reese's Pieces stuff, the distribution of the population is all the candies in all the machine. So if I made a dot plot of this based on color, one dot would be one piece of candy, all right? If I was plotting how many orange are in there. Now the distribution of the sample is this subset of the population down here. And again, if I made a dot plot of this sample, each dot would represent one piece of candy. Sampling distribution of the sample proportion, however, I'm taking a proportion. I'm taking a percent of how many are orange. That's what I was interested in this problem. What percent of my sample is orange? Well, one sample, I calculate 1%, and that 1% becomes one dot on the dot plot. So what this represents here, notice there's a lot of dots. That means it took a lot of samples and calculated what percent of orange from each one of those samples. That's what the sampling distribution of the sample proportion looks like in this situation. But the biggest idea here is that each dot represents the percent from one sample. So describe what we know about shape, center, and spread of the sampling distribution of a sample proportion. Okay, these are overall generalized rules that work for shape, center, and spread. First of all, the shape is sometimes approximately normal, but it depends on the sample size and the population proportion that we're given. And that's something called the large counts test, which helps us determine this, and I'll explain this in the next slide for you. But shape depends on your sample size and the population proportion. Now what about the center? If I took a bunch of samples and distributed or put them on my dot plot, where would they center? Where would the balance point be? Well, the mean of the dot plot is approximately the same as the population parameter, since p hat is an unbiased estimator of p. All right, so what does that mean? Well, we talked in the previous video about biased versus unbiased estimators. One of the unbiased estimators we use in statistics is proportions. And we know that if we take a bunch of proportions from samples and put them on a dot plot and find out what's the average of all of our proportions, that average is going to be very close to the true population proportion. So we can say that mu of all the p hats, the mean of all my proportions, is going to be approximately equal to the true population proportion, which we use p for. What about spread? For a specific value of p, the standard deviation of p hat, standard deviation of all my p hats, gets smaller as n gets larger. And there's a formula for this that I'll show you on the next slide. Alright, so when is it okay to say that the distribution of my p hats is approximately normal? Well, we use the large counts condition or large counts test, either way. And it looks like this. It's the sample size times the population proportion. If that's greater than or equal to 10, and then I can take the sample size, multiply it by the complement of a population proportion, and it's greater than or equal to 10. If both of those are true, then I know that the sampling distribution of my sample proportions is approximately normal. And that's a mouthful, I know, but that's the test that we're going to use to determine normality. So what are the mean and the standard deviation of the sampling distribution of a sample proportion? So what are the mean and the standard deviation of the sampling distribution of a sample proportion? Well, the mean looks like this. We said it's an unbiased estimator, so the mean of all my p hats will be approximately equal to the true value of p, whatever the proportion is of the population. The standard deviation looks like this. It's the square root of p times the complement of p divided by the square root, or divided by the sample size. So these are on your formula chart. You don't have to memorize them. You just got to know what they represent. It's the mean and the standard deviation of a sampling distribution of a sample proportion. Now, are there conditions that need to be met for these formulas to work? There is. You can only use these formulas if the 10% condition is met. Okay, remember 10% condition, that n is less than or equal to 1/10 of the population. So let's try one of these. The superintendent of a large school district wants to know what proportion of middle school students in her district are planning to attend a four-year college or university. Suppose that 80% of all middle school students in her district are planning to attend a four-year college or university. What's the probability that a simple random sample of size 125 will give a sample proportion of, at most, 75%? Okay, so when you're reading a stats problem, you're going to have to decode a lot of stuff here. So let's kind of look at this. This 80% says, suppose that 80% of all middle school students, notice it says all. That means that's the population parameter. So it's P. P is the 0.8. That's all middle school students. Now, notice she says it's a large school district. She doesn't give us a number. We don't know how big the population is, but we just know it's large. All right, that's important for later. Then, the simple random sample of size 125. That's our N value. Okay? Next, is it independent? Well, we got to know if it's independent before we proceed with the rest of this. Remember, our formulas depend on independence, the 10% condition. So if I check that 10% condition and I say 125 times 10, is it less than or equal to what they called a large school district, which is 1,250? Well, I would assume a large school district would have way more than 1,250 students. So you're using a little logic here, and they didn't give us a distinct, clear answer. But it's reasonable to assume that that district's larger than 1,250 people. So we're going to proceed as if this is an independent sample. So then we have to know what's the center of the sampling distribution. If I took a bunch of samples of size 125 and found the percent who are planning to attend a four-year university, where would the center of that be? Well, we said it's going to be the same as the population parameter, which is P, so it's 0.8. The spread, we're going to use this formula right here, and for P, we're using 0.8. So 1 minus 0.8 gives me 0.2 over the sample size, take the square root, and I get this value. This is my standard deviation of my sampling distribution of the sample proportions. Now, the question asks us to find a probability, but I need to know what shape this is. Is it normal specifically before I can proceed? So I have to do the large counts test to check that. So n times P has to be greater than or equal to 10, and n times the complement of P has to be greater than or equal to 10. So I run the numbers. 125 times 0.8 is 100. That's more than 10. 125 times 0.2 is 25. That's greater than 10. So because they both are greater than 10, it passed the large counts test. That means the sampling distribution of p hat is approximately normal. It's not exactly normal. Don't just say it is normal. It's approximately normal. And don't just say population is approximately normal. It's not the population. It's the sampling distribution of p hat. I know the words matter here, guys. All right, now I want you to pause for a second and look at the work I'm showing. All the work I'm showing is necessary. You have to show me this. Don't just say. Now, you don't have to do this portion right here with all the symbols, but you do have to show me this. And don't just say equals 100, equals 25, check it's good. You have to have what we're comparing it to, that greater than or equal to 10 in there. Now you may ask, okay, what if it doesn't pass the large counts test? What if it doesn't? What do you do? Well, you would have to do a simulation or a binomial distribution to help us find the probability. Okay, 99% of the time it's going to pass that large counts test. You just have to prove it. All right, but that's what you need to know if it doesn't pass. All right. Back to the question. So what is it really asking us? It's saying, what's the probability that a simple random sample of size 125 will give us a sample proportion of at most 75%? So that translates to this probability statement. That the proportion, or probability, the probability of a sample proportion is less than or equal to, that's what at most means, 0.75. All right, now think of our distributions. We've said it's normal. We've proven it's approximately normal. So I can use the norm CDF function. My lower bound is negative 10,000. Upper bound is 0.75. My mean is 0.8. Standard deviation is 0.36. And I crunch up my calculator, I get a probability of 0.0824. Remember, that's the probability of getting a sample proportion of at most 75%.